Hello, welcome to UGC NET Online Pre-Coaching. Today I'll discuss very important concept, theory of computation or finite automata. Most of you requested to make some videos based on finite automata because most of the universities not included this subject as a compulsory subject. That is the problem. But finite automata and theory of computation, it's very useful uh, in computer science subjects. It may be net or gate or any other computer science subjects, but today I'll go through it step by step complete. I'll try to um, make it clear all the doubts. Actually, only this subject you will get a very simple questions, but most of you unaware of this subject, not possible to attempting these questions. In First of all, I'll explain theory of computation. What is theory of computation? What is automata theory and all? And later on, I'll solve June 2018 question number 31 to 40, 10 questions based on finite automata. Okay. First of all, theory of computation. Before starting this subject, we need to remember. We need to try to know the one of the greatest computer scientists or mathematician, Alan Turing. He is the um, in 1939. I'll go for a little bit history. He's Alan Turing. He's the great mathematician. He has he has worked in Second World War for US and UK. Uh, he has developed one small machine, that is Turing machine. Name of the mathematician, Alan Turing. His name only kept that machine. He has developed that machine basically to uh, decode and encode the signals. Later on, that machine, more powerful machine, today's whatever computer we are talking, whatever supercomputer, only outcome of that Turing machine. Okay, I most of the questions, out of 10 questions, based on 3-4 questions, or sometimes 6 questions based on Turing only. We'll see one by one. First of all, there are finite machines. We need to understand what are the machines available before computer. Okay, today's also it is using for PDA machine and Turing machine and all. There are um, these are deterministic finite automata, Pushdown automata, linear bounded automata, and Turing machines. Okay, first of all, understand what is finite state machine. A finite state machine is a computational model that can be implemented with the hardware or software and can be used to simulate sequential logic and some computer programs. Finite state machine generates regular languages. Finite state machines can be used to model problems in many fields including mathematics, artificial intelligence, game, and linguistics. Means what? Finite, you can understand based on this one only. It has a wide scope. It has a wide applications in many fields. First of all, in machines, um, actually there is some questions like regular language. What is regular language and all? I'll explain in next slide. These are the machines. Combinational logic is a subset, uh, part of finite automata machine. Means finite automata machine can read regular language. Okay, Pushdown automata is a some extended version of finite automata. Later on, I'll explain how Pushdown automata is differentiate for finite state machine, and Turing machine is more powerful than finite automata. Okay, so this is simple one diagram. This is the initial state, and if you turn on and off like a button, it is in electronics. Like it can use many purpose. Means what? You can model many real applications in finite automata. Then, before understanding in detail for machines, first of all we will go for Chomsky, one of the greatest one more mathematician or philosopher, Noam Chomsky. He has derived uh, types of language. Means what? Chomsky hierarchy of the language we call this one. Here regular language, it is a small circle, this represents a regular language. Regular and context free language, this is a regular language subset of context free language. There are some restrictions. And context free grammar, next context sensitive language, this is better than, means what, these two are the subset of this one. And recursive enumerable language. Okay, means in this subject you need to understand four types of languages and four types of machines. Okay, then I will go for next slide. I will explain in detail. There are type 0, type 1, type 2, type 3. There are four types of grammar. Here grammar accepted by type 0. Type 0 grammar accepted by that is unrestricted grammar, means what, it can, there is no restriction in this grammar. Usually we will call this language is recursive enumerable language. This one accepted, Turing machine can read only, Turing machine can read this language. Other than this, any type of machine cannot read this recursive enumerable language or unrestricted grammar. Okay, this is type 0. Now type 1 grammar, this is context sensitive grammar. This is context sensitive language. Context sensitive language generates from context sensitive grammar. This one reads linear bounded automata. If you know this table perfectly, you can answer 3 to 4 questions without knowing complete subject of finite automata. So you will came to know in this presentation only. Type 2 grammar accepted context free grammar. Context free grammar generates from context free language. This one reads Pushdown Automata. Similarly, type 3 grammar, it is a regular grammar. It accepted by regular language. This is reads Finite Automata. Means what? Finite Automata reads only regular language, but Pushdown Automata can read context free language. Some restrictions, it can read regular language also. But if you both restricted both the sides, I will explain. I will show you what is exactly Turing machine. Later on I will explain. Linear bounded automata, this can read context free grammar language, also context sensitive language. But Turing machine can read all the languages. This is the power of Turing machine. Still anyone achieved highest means equivalent uh, Nobel equivalent prize in computer science, that is Alan Turing prize. So this Alan Turing has designed this machine. This machine has the capacity to read all the languages. So that's why Turing machine is more powerful than other machines. So please be clear. Four machines: finite automata, Pushdown automata, linear bounded, and Turing machine. Four languages: regular language, context free language, context sensitive language, recursive enumerable language. So regular language type 3 grammar, means type 3 grammar, also called as regular language. Sometime it will ask this question also. Type 2 is context free language. Type 1 is context sensitive language. Type 0 is recursive enumerable language. Okay, now we'll move to, this is exactly Turing machine. So this is working of Turing machine. Just it is a 1 minute video. This is how exactly Turing machine is working. Just how it's working. This is read write head. It is read head, erase. It can write 0 or 1. This is Alan Turing machine. Read write head with eraser. This machine is developed in 1939-40 round in Second World War. This machine used to encode or decode the signals, whatever communication signals used uh, to decode signals. Use this machine. This is very useful in Second World War. That's why it is very popular also. This is actually Turing machine. For example, this is a machine start state. This is halt means end state. What which language it can read, that is it shows like this. For example, here a b a b b b a b, it reads or not, just checks it. This is this one. A reads here, b reads here, but not a, so you got a error. If it is a b b b b b and stops, then it is accepted. A, it reads self loop. This is exactly working out Turing machine. Then we'll move to question. First question is, I hope now you are clear. There are four languages, there are four machines. Finite automata, just go through 1 second. There are four machines: Turing machine, linear bounded automata machine, and Pushdown automata, and finite automata means finite state machine. Regular language, context free language, context sensitive language, recursive enumerable language. Okay, these all are type 0, type 1, type 2, type 3 grammar. Okay, then we'll move to first question. Two finite state machine are said to be equivalent. They are, means what? If it is two finite state machines, like a finite like you take a DFA, is said to be equal, means what? Have the same number of edges. Edges means, for example, in this is represented, this is the nodes, but anyhow it's not possible to tell edge based. And also have the same number of states, maybe, may not be. But usually finite state machine used to recognize the tokens, means in compiler design, first of all, first step of the compiler design, recognize the tokens. Okay, any language, any C language, C++, you go for any programming language for compiler design, first step is to recognize the tokens. So recognize the same set of tokens. So two finite state machines are said to be equivalent if starting from uh, their respective initial states, they will produce the same output sequence when they are given the same input sequence. That implies they must recognize the same set of tokens. If it is two equivalent machines, both are equal, if you give both same set of inputs, you will get the same set of outputs. So definitely recognize the same set of tokens. Okay, you can go for one more definition also. So answer C is right. Then go for finite state machines given in figure. This is a finite state machine. So actually this symbol indicates start state, this symbol indicates end state. For example, if it is starts, reads A, reads B, means what? 1A 1B, it stops, means what? 1A 1B. Here in this direction 1B 1A means AB or BA. Okay, now look at any string of odd number of A's. It's here not only odd number of A's, here one more B also. It's not possible to only recognizing A, it's not possible to reach. Okay, so any string odd number of B's, only recognizing B, it's not possible to reach a end state. So means what? At least it requires A and B. It requires A and B means what? First rolled out first two options, come to the third option. Any string of even number of A's and odd number of B's, even number of A's, odd number of B's. Go for first step only, you came to know 1A 1B you can reach, 1B 1A you can reach, means what? 1A 1B So any number of odd number of A's, odd number of B's, 1A 1B you can reach. Look at 1A 1B. If you go back, B means 2B, come back, B means 3B 1A, means it requires odd number of A's, odd number of B's. So any string odd number of A's, odd number of B's. If you check this one, you can go this website. I will show you how exactly working of this one. This is a website. You can go and put, for example, I will select here example is even number of zeros. How it is reading exactly your finite automation meta machine, even number of zeros. For example, I will give odd number of zeros. Load this one and run. It reads 0 q1 is changing states also, you look at. So rejected, because actually it reads even number of zeros, but here odd number of zeros, it rejected. For example, if you give 6 zeros, load and check it, here changing the state, there are 6 number of zeros. When it is reads empty string, it stops, accepted, because a total number of steps are to read 6 zeros, 6 steps, 1 null state, that is 7 state steps required to find a number of zeros. Okay, here I will give 2 ones here. Okay, reads it 1 0 2 0 3 0 4 0 5 0 6 0. It reads 2 ones, no problem, but the question is even number of zeros, it accepted. Okay, there is no question related to 1. So every total this question is related to zeros. So you can go, you can check palindrome or not, number of divisible by 3, decimal to binary. There are so many examples. You can go and check how exactly finite automata or finite machine it works. You can go through this one, you can easily understand. Now we'll move to question number 33. A Pushdown automata behaves like a Turing machine when the number of auxiliary memory is. Actually, Pushdown automata, before explaining this one, I will show you Pushdown automata. This is Pushdown automata machine. If this is additional memory in the finite automata, if you remove this additional memory, this is a finite automata. Means what? It reading a number of just whatever memory it is reading, A's and B's, whatever string it stores in the memory. But if we add extra memory to remember, to count, that is stack memory, if you add this one, this is a Pushdown automata. If you not added, that is a finite automata, just for a deterministic finite automata. Now this question, this problem is, if you read A and B in left or right, actually it is reading one way. A finite automata reads one way, Pushdown automata reads one way. If you read one way, this is like a only push into the stack, and if you want pop, if you want push and pop operation to remember, usually for example 3 A's 3 B's, means what, the given number is palindrome or not, like that you need to number of A equal to number of B. To count that one, you need to push into the stack, or number of open brackets equal to number of close brackets in the program is there or not. To check that one, use this Pushdown automata in compiler design. Okay, that's why if it is open left and right, if it is open, then obviously Pushdown automata behaves like a Turing machine. If a Turing machine can read any, there is no restrictions. That's why a Pushdown automata behaves like a Turing machine when only 2 or more auxiliary memory, means what, only one auxiliary memory. It's not possible to behave like a Turing machine, means what, Pushdown automata not possible to work like a Turing machine if you have only one auxiliary memory. If you have more than 2 auxiliary memory, then Pushdown automata also work like a Turing machine. This is the meaning. So Pushdown automata behaves like a Turing machine when the number of auxiliary memories 2 or more auxiliary memories. Here only one auxiliary memory, so it is not a Turing machine, it is a Pushdown automata machine. Then we'll move to Pushdown automata can recognize the language. Just now I have explained, already I have given a table. Pushdown automata can recognize the language, context free language or regular language. Just now I explained here in first slide. Turing machine can recognize all languages. Linear bounded automata recognize context sensitive, context free, regular language. Pushdown automata machine can recognize context free language and regular language. Finite automata machine only reads a regular language. I will go to for showing 1 second. If you know, that's why initially I told you 1 minute. Initially I told you, if you know the table, sorry, 1 second. If you know the table, just a minute, sorry for sorry, just a minute. Okay, just if you know this table, you can easily understand. Push to, just a minute, sorry for, okay, here look at, sorry for disrupt. Finite automata machine can read a language, only regular language. Pushdown automata can read these two languages. So linear bounded automata can read these three languages. Turing machine can read all four languages. This is based on this one. They asked one question, that is 34th question. Pushdown automata can recognize context free grammar or regular grammar. It can read both the languages. Okay, this is 1 second I have given you. Then go for 35th question. To obtain a string of n terminals from the given Chomsky normal form grammar, the number of productions to be. Okay, just now I explained what is Chomsky normal form. The given string, for example, I'll show you next question, also cover same thing. This is a grammar. It always starts with the starting symbol s, and it tends to starting means non-terminal symbol. Yes, capital letter represent a non-terminal symbol, small letter represents a terminal symbol. Okay, so then now let n be the length of the string. We start with the non-terminal symbol s, which has length 1. So you look at here, this is 36th starting symbol, this is non-terminal symbol, this is a b are the terminal symbols. Here using n-1 rules, non-terminal symbol reads non-terminal to non-terminal. So total n-1 non-terminal symbols we are using. We can construct a string containing n non-terminal symbols. Then on each non-terminal symbol of said string of length n, we apply a rule from non-terminal to terminal. Means what, every non-terminal symbol should terminate with the terminal symbol. So for this rule, the total number we apply, starting symbol s is n, so non-terminal symbol n-1 plus n terminal symbols, total 2n minus 1 productions rule. Then the number of productions to be used, 2n minus 1. This is your 35th question. 36th question, consider the following grammar. This they have given two grammars. Don't think it too much related to this one. There are simple thing is, the G1 is ambiguous or G2 ambiguous. First of all, this grammar, it generates S starts and it generates SBA. I'll explain what is ambiguous with one example. This is ambiguous. A string X is a language from G may have two or more parse trees. Means what, this given string, it generates two or more parse trees. One single production or single given production, it can generate more than one type of tree, then it is called a parse tree. So for example, starting symbol is it generates from SBA. This is SBA. Okay, then one S is, it maybe takes A stop. This is terminal symbol. This S may starts again SCA, and this S terminates A. This S terminates A. Here capital S represents a non-terminal, small letters represents a terminals. Same thing, S, it may starts here or it may starts, S starts from SCS, S starts from SCS. Here this S means what, right side of S stops now. Here left side of S stops first. Here right side of S stops first. Okay, here left side S generates one more time SBS, this one, so stops. Finally you will get AACA, here ABACA. This is means what, this tree can generate more than once, that's why it is, the given grammar is ambiguous, means what, it can generate two or more same trees, parse trees, that's why it is ambiguous. Here now come to the question 36. This one you need to check, and also this one you need to check, as like a tree, you draw the tree, definitely it generates both more than one parse tree. So this is both G1 and G2 are ambiguous. Just you go for this rule and try to draw your own tree, then definitely you'll get the question G1 and G2 both are ambiguous. So option C is right answer. So now we'll move to 37th question. Context sensitive language can recognize by, look at, same only one table in 2018 June, they asked 4 questions. Here context sensitive language can recognize, now you can easily tell linear bounded automata, because finite state machine reads only finite automata, regular language, deterministic finite automata, regular language, non-deterministic finite automata, regular language. This is finite state finite automata reads only regular language. Only linear bounded automata can read regular language, context free language, context sensitive language. So if you know that table, you can easily answer one more question. So look at, it's a very simple question solve if you know only one table properly. Okay, this is this given set, they have given one set is an example of this grammar. Here number of n, for example n, they have given a set of n takes 1 2 3, there are so many, let us assume n is equal to 2, means what, 2 zeros, 2 ones, 2 twos, means what, you can count number of zeros equal to number of ones equal to number of 2, then only it is true, this grammar. But how do you count? This is not possible to count in a regular language, because there are 3 set of different sets. Okay, if you request again, I will make one more video based on this one, how exactly I will go in deep, or else if you understood this much here only, no problem. If you have confusion, just comment in comment box, I will make a video. Okay, here to read finite regular language, it is not possible anyhow. Go for context free. Context free means what, if you palindrome or not, means number of zeros equal to number of ones, or number of a is equal to number of b's, number of open bracket is equal to number of closed bracket, you can use context free. But here number of zeros is equal to number of 1, if it is only this much, you can go for context free. Number of 1 is equal to number of 2, go for context free. But here 3 elements you need to compare, then go for context sensitive language, or else better go for Turing machine. For given 3 options, we'll go for context sensitive is the right answer. Okay, here seeing you can push on to the stack, seeing you pop out of the stack, essentially comparing number of ones equal with number of zeros, obviously number of zeros with number of twos. You can do this one using context free, but hence it is not context free language, it cannot be accepted by Pushdown Automata. it needs linear bounded automata to read this context sensitive language. So answer A is right. Now we'll move to an answer. Question number 39. A bottom-up parser generates usually. Please remember this one. This is in language hierarchy. We will study one more thing here. Usually, I will tell you. In general, if you don't know much about finite automata, at least you remember this one. But bottom-up parser always rightmost derivation, it generates rightmost derivation, and top down parser, it generates a leftmost derivation. At least you can roll out, if you know this much, you can roll out two options. Bottom up parser means what? Obviously it is not a leftmost, it is not a leftmost. Rolled out 1 and 3. Now you have two options: rightmost derivation tree or rightmost derivation. So rightmost derivation in reverse or rightmost derivation. To know this one, you can understand, at least you try to roll out two options. So bottom up parser starts from the leaf nodes, means end of the bottom of the tree. Means what? If it is a tree, it starts here reading, parsing like means leaf node to root node. But if it is a top down, root to leaf node, like that. Actually tree works in upward direction till reaches to the root node. Here we start from a sentence and then apply the production rules in reverse manner in order to reach the start symbol. The image given side, whatever given here, bottom up parser available. These are the bottom up parsers available. To bottom up parser generates the rightmost derivation tree in reverse order. Okay, this is option 2 is right answer. So if you know better, try to know what is exactly rightmost derivation, what is exactly leftmost, when it is generates, when it is you can if possible I will make one more video based on this. I hope at least you will get a glance how exactly you can eliminate two options. Okay, so 1 second I will tell you. Bottom up means always rightmost, it may be rightmost reverse or rightmost derivation. Top down means leftmost derivation. At least you can rule out two options. Then if you read one some more some additional, you can roll out one more option. Okay, so last question. Consider the following statements. There exists no algorithm for deciding if any two Turing machines M1 and M2 accept the same language. There exists no algorithm for deciding if any two Turing machines M1 and M2 accept the same language. Okay, this is a question. Obviously, still today, even though fastest or supercomputer, still there is no algorithm to decide the existing means two machines accept or not at the same time. Also one more question, one more option. The problem of determining whether a Turing machine halts on any input is undecidable. Yes, obviously still we don't know the answer of these two. These two he has explained in 1942, Alan Turing, what is the capacity of the computer, even though supercomputer still working whatever he explained. What he means in Alan Turing explained in detail what can computer do, what it cannot do in detail. What he has explained in 1940 round. Still today's fastest computer works in that principle only. So obviously great mathematician and also great computer scientist. uh, 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 Today I have remembered him. And also I hope you have seen nearly 5 questions based on Turing. So now you can you got some confidence to solve finite automata related questions. I hope you enjoyed this video lecture. If you like or dislike, please, if you have any comment, just message in comment box. Thank you one and all.